Good morning, people, or whatever time of day is appropriate. Today we start to talk about rotational acceleration and a new formulation of Newton's second law. Now, as you may remember, Newton's second law is about the factors that affect or control a system's acceleration. Well, from a linear or translational point, the question is what controls a linear system's acceleration? Well, as you hopefully remember, we have a way of expressing what a system's acceleration is equal to that is what's called Newton's second law. We typically don't see it solved for A, but we say that acceleration is directly related to the net force applied to an object and inversely related to its mass. We see that most typically expressed as net F equals ma. Okay, fine. Now, what controls a system's angular acceleration or rotational acceleration, right? This is linear, translational. What you sometimes, my people sometimes hear me say is along a path, as opposed to here, which we mean about an axis. All right, well, what you should be okay with so far is that we have angular acceleration alpha, and, well, it's not just force that makes things accelerate angularly about an axis. Well, it's net torque. People know that when we say objects are in equilibrium, right? Our equilibrium statement for here, equilibrium, is that net force is zero because, well, that is the same as saying things don't accelerate. Well, my peeps know that equilibrium on this side, on the rotational side, doesn't mean that net force is zero. It means that net torque is zero. And that means that angular acceleration is zero. All right, but we still have this sort of other thing hanging out here. Well, it's not just mass what goes here. Because we say that, well, net torque is something times alpha. Like something, and that's this question. What is this rotational analog of mass? All right? From a treating things as point masses perspective, all that matters is the mass of an object, how resistant it is to acceleration, how much inertia an object has. All right, but when we get to this side, the rotational side, there's more to it than just how massive an object is, because now objects have shape, right? And their mass can be distributed in different ways. So there's this analog of mass that we put into Newton's second law from a rotational perspective, or in a rotational context. All right, to figure that out, what I'll do is give you a little situation to consider. Okay, so let's take the example of this object, which I know I've drawn as having size, but let's assume that it is a point mass. It has a mass m. Can you see that? Yeah. And it's attached to a massless, that's real important, a massless rod of, oh, I don't know. Well, it doesn't really matter, I suppose. It does matter, but just keep going. And it's released from that initial orientation. All right, so this system, and by system I mean the massless rod and the point mass, when we release this system, well, the system does not have a linear or translational acceleration. All right. If that were to be the case, then every part of the object would have to accelerate in the same direction. All right. But like this part doesn't accelerate at all. It doesn't move at all. But what we can talk about is the linear or translational acceleration of mass m. All right, and to do that, all we have to really say is when this thing is released, this object is released, there is a force mg that acts on it. Right? Sure? Yeah, great. Now, at the instant that it's released, well, we just say that mg equals ma. All right, fine, great. And that this object accelerates with free fall acceleration. Now that happens just for the first instant until this object, the rod here, has to start exerting a force on the ball, the point mass, to keep it moving in a circle. All right, so this is at this instant. At the instant just after it's in this, or just while it's still in this horizontal orientation. Now, from an angular or rotational side, here's what we can do. Let me go back to this. If I take this and sort of start with that force statement, but then what I do is just say, well, let's say that this is a distance r. And I do this and just decide that I can multiply both sides of this expression by the same common factor. There's nothing wrong with doing that. Well, I've now turned this into something. R times mg. Well, that's a torque, right? And not only that, it's the net torque. It's the only torque produced or acting on this, produced by any forces on this system. All right? And, well, what we get is equals MAR, but I want to talk about angular acceleration instead of linear or translational acceleration. Well, this acceleration is in this direction, which happens, now notice, when I actually let this thing go, it does this, it moves in a circle. So this direction at this instant is an important direction. It's a tangential acceleration. And what you have to be able to do here is go back a few days and say, well, if I want to connect tangential acceleration to angular acceleration, we say that AT is R times alpha. And for this object that's at radius capital R, we turn this into M R alpha times that alpha. And we say that net torque is M R squared alpha. And well, now you notice that we have net torque and alpha, and we have this other thing that sort of relates the two. Remember we were saying we know net force is ma, there's Newton's second law. We want net torque is something alpha to give us a new formulation of Newton's second law. Well, here it is. But we don't just say net torque is mr squared alpha, because this mr squared expression is only true for a point mass moving in a circle of radius r. All right, but what it does sort of say is that we can relate net torque and alpha with this sort of, in general, an expression that talks about not just how much mass an object has, but how that mass is distributed. All right, because objects now have shape, or systems aren't just point masses. And so what we call this there's this rotational analog of mass, and it's called two things. You'll see it both ways: moment of inertia and or rotational inertia. Those are the same thing. And that is the variable capital I. And for a point mass, apparently, the moment of inertia, the rotational inertia, is mr squared. Where, again, a point mass can only move in a path, so this is radius of path. And that also means that moment of inertia has units that are, well, this is kilograms times meters squared. Therefore, the units of moment of inertia, or rotational inertia. All right, so in general, In general, I'll go back here and we say that this new formulation of Newton's second law for systems that rotate, his net torque is I alpha. Or the system's angular acceleration is directly related to the net torque that it experiences and inversely related to its rotational inertia. Okay? Let's talk a little bit more about rotational inertia. Here is a 3. You really want to calculate? I guess. Here's an object that revolves about an axis, and it's a point mass, and we have a radius. So this thing's moment of inertia is just mr squared, and that's 350 grams. All right, well, I can just leave that and turn it into this times 4 square meters. 2 meter radius. So that's, of course, that's I is, 1.4 kilogram meter squared. Sure. Why not? Now, 2 point masses revolve around an axis as shown. Let's give these some generic M1, M2, and at, say this is R1, and this is R2. So this, M1 moves in a big circle like this, and M2 moves in a smaller circle like this, and somehow they're, maybe they're connected. It would probably be best if they were connected by a massless rod. Actually, doesn't matter. It's massless and it's not even really there. The system's moment of inertia, I system, equals the sum of all the moments of inertia. And so that's I1 plus I2, or M1 and M2. So I system is, well, we got M1 at R1 squared, and we have M2 at R2 squared. Duh-ish. Okay? So when there's not just an object, but multiple objects, a system's moment of inertia has to account for, well, the distribution of stuff, where it is, what it looks like, how massive it is, not what it looks like, but where stuff is and how massive stuff is. Okay? However, you see, maybe I'm getting, yeah, sure. So here's the deal. Yeah, we'll just go here. Different objects, and these are some of an infinite number of different kinds of objects, but here are some different objects. They have different moments of inertia. Yeah. Where do these come from? They come from integral calculus, to tell you the truth. There's a way to say, well, never mind, I won't go away with it all, but it's really sort of doing this. You say, you look where each thing is, well, where each thing is, and you do a sum of all the objects in the square of their position. And so that turns, when you say sum, S-U-M, sum, that ends up meaning you do what's called an integration. And the bottom line is, based on where the stuff is located in, say, a solid disk that rotates about an axle down its center, or cylinder, the moment of inertia happens to be 1/2 mr squared, where this r is not a radius of the cylinder's path, it's the radius of the cylinder. All right? All these are radius of the object, not any path thing. Radius of object, radius of object. Look, a shell as opposed to a solid sphere. And then when you get to things like this, like this stick doesn't have a radius, but it has a length, right? This is a length L. Here's a length L. All right, so you don't have to memorize these. You'll have to apply them. All right, here's a disk. It's pretty rare that we do these where you're taking a disk and flipping it around that axis. It's much more common for us to use disks that we rotate about this central axis. And notice that a disk is just a skinny cylinder. They're both 1/2 mr squared. All right. And so what, I guess, so what is like, you could say, now here's a more complex sort of system where this is a rod, an actual rod of mass m and length L, and this is an actual sphere because it has a radius. So here's radius r. So that's not a point mass anymore, that's an actual object. And this system rotates about this axis. And what we want is its total rotational inertia or moment of inertia. So we say something like the following. Well, I system is, what do we got? We got a rod end, a rod about its end, right? Because that's a thing. And then we have, this is hard because what we have here is a sphere about any line that goes through its center. It's like a rolling ball. That's not quite what this thing is. All right, what this thing is an object that does actually travel in a big circular path. So in that sense, it's like a point mass, right? But what you also have to imagine is here's a place on that sphere. Well, when that sphere is over here, that place is over here now. So what happens is, as this object, or as this whole system rotates about this central axis, this sphere on the end is two things. It's a point mass, and it's a sphere that rotates about a central axis. Now, by that I mean like about, it sort of rotates about that axis. You get me there? Quite literally, if this point was on the sphere's right, and now this point is on the sphere's left, well, it's like the sphere rotated. So this is a tricky part here, where we actually have to say that when an object goes through, rotates around some different axis that's not through it, you kind of have to treat it as two things. A part that moves in a circle and an object that rotates on its own center. That's going to be hard, I get that. So this thing, the proper expression is, let's see, a rod about its end is 1/2, well that's little m. I say 1/2, 1/3 ml squared. Now, the point mass part of this sphere motion is, well, m. And, well, normally we'd say mr squared, but r means, remember, r means the radius of the object's circular path. And this object has a circular path with a radius L plus r. You get me? Here's L from here to here, and then here's R from here to there, the radius of the actual sphere. And then we say that the sphere rotates about some axis, and a sphere, solid sphere about some axis, has a moment of inertia 2/5 mr squared. So we gotta add 2/5, and this thing does, the sphere does have a radius capital R. So that's an expression for this entire system's rotational inertia. I get it. This is a tough part. Because that sphere has two elements of its rotational inertia. Okay? Okay. Yeah, bottom line, big deal. When an object accelerates in a straight line or travels along a path and changes direction, or some of both, when an object accelerates along a path, net force equals Mn. All right. When an object rotates or a system rotates about an axis, there's and has angular acceleration, then we say net torque is I alpha. All right. One of the challenging parts is what's the appropriate expression for I. All right. So it'll come in the form of the question. It'll say a sphere, hoop, disc, blah, right? Something like that. So a couple of looks at application sort of stuff. Let's say we're going to open a regular door, and by regular I mean there's a hinge at the edge. All right, and if we apply a force F at the end of the door, you push here. Let's say this door has a width W. Applying a force F at the end produces, well, you can probably answer that a couple of ways. One is torque, net torque, and therefore angular acceleration. All right, so I would say here that net torque is I alpha. Our net torque is F times W. The rotational inertia of a door, it is really the same thing as a rod about its end, right? Here's the front view of the door with the door handle and the window, and we're saying about this axis. Well, it doesn't matter that the door has this dimension. All that really matters is this dimension. So if we squish this whole thing down to say, well, the door just looks like that, and all we care about, like we said, is this dimension, the width of the door. Okay? Rotationally, we don't care if the door is, 40 pounds and is 6 feet tall, or 40 pounds and is an inch tall. Still the same difficulty in making it accelerate rotationally. So anywho, door about end is rod about end is, there we are, 1/3 ml squared. So 1/3 m, well, L is actually for us W. So there's I and then alpha. Well, notice we get rid of a W and a W, and we get an expression for this door's angular acceleration, which is 3F over mW. Yeah? Now let's change the way let's look at a different door completely, a door that has a swivel in the center. But everything else about it is the same, all right? It still has a total width W, and it has the same mass M. All right. Well, let's see. Let's make the criteria that we're going to give this door the same angular acceleration. Well, and let's also keep the criteria that we apply a force F prime at the end. And the question is, how big does that force need to be to achieve the same angular acceleration? Well, I'll give you another net torque equals I alpha. Now our net torque is now F times, well, W over 2. Right? Because here's our vector R from the point of, for the axis of rotation to the point of application of force F. That's W over 2. Now, the rotational inertia of a door about its center or a rod about its center is here, 1/12 ml squared. So that's 1/12 ml squared. We still do use the entire length of the rod, in this case width of the door, and alpha. Okay, all right, very good. Looks like we still get rid of one of these and those. And then we get to, oh, this is F prime now. Remember F prime.
Good afternoon. Sorry for the.
All right, so we have, here's what we have now. F prime over 2 is 1/12 mw alpha. Well, I want to get the same alpha as before. So I'm just going to say that this alpha is 3f over mw. Original F, here's F prime. All right, so let's do a little of this, and well, these can go and give us a 4 here, and then we get F prime is, oh, well, wait, then we can get rid of the M's and the W's, and we get 2, F over 2, F prime over 2 is F over 4. Yeah? Okay, F prime is F over 2. Fair enough? Okay, I think that's a good place to wrap. Here's what I'd like you to do. Yeah, here's what I'd like you to do. This is about this assembly here. Not an assembly, it's just a disk. That's important. And there's a radius here, capital R. And of course, FE acts like this, let's say, on the disk's edge. 1, give me an expression for angular acceleration. Not too bad. 2, another force, I don't know, just plain old F, not FE, just plain old F, is applied somewhere on this line, such that the disk no longer accelerates. No longer accelerates. Generate an expression for how big that force must be. We have to define that this has a radius little r. And then we change the magnitude of that force to something else, but it's still applied along that dotted line. Come up with a new expression for what the system's angular acceleration must be. All right, and all your answers are only in terms of m and r and f's. Okay? I'll see you with that when I see you next. If I see you next. Peace out. Peace out.